why do we study this? And I think it's kind of been popping up, right? I'm hoping that you're starting to see why we use these functions. When we looked at sketching these quadratics, it's really important to know these because we use those to solve quadratic inequalities. When you are solving equations with unknowns in the denominator, sometimes we got cubics. And it's very difficult to solve these cubics if we don't know what it looks like. The graphical approaches are much more powerful than algebraic ones. They're much less error prone as well, right? Now I know, like from the general equation, what happens with this plus 8? What's that actually going to do? It's going to shift it up. Yeah, that's right. So you can actually draw this really easily now. Like before you'd have to use a table of values, but once you know the relationships and patterns that are happening, you can just say, hang on, well, I know that this is just my normal cubic shifted up 8 units. And that's all you have to write. Okay? That's my graph. Easy, done. What is the domain and range of this graph, though? So remember, what are the domain ranges? Domains are the x values where my graph is defined, and the y values are where the range is my y values where they're defined, right? Yeah, so even though I don't have the whole thing here, these graphs, these arrows mean they go on forever. So they're going to go all the way up and down, and they're going to actually go all the way left and right as well, because there's no kind of asymptotes, or there's no place where it's like restricted, like the quadratics, right? They're going to just keep on going forever, kind of like your linear function, but this one's a bit curvy, right? So it'd be, as you said, negative infinity to infinity.
Is it like that for all?
And same for the range. Is it the same for all of them?
Maybe.
We'll see. And last one, right, solving cubics. Well, I'm solving for f of x equals 0. We have this notation now. I know that means that I've got x cubed plus 8 is equal to 0. How can I solve this? I'm trying to solve this equation. And how do we usually solve equations? Yeah, trying to get x by itself. And like we only introduced equations, we said, oh, I want to get x by itself. That's what I want to do here. So, yeah. So what's the opposite of whatever this is? Yeah, so x cubed equals negative 8. Now hang on, does this look like a problem?
No. You can cube it.
Ah, okay. So you're kind of so well trained that when you think about quadratics and you see a negative on the other side, you're a bit wary because rightfully so, you can't take the square root of a negative value. But interestingly, with cubes, can you put in the cube root of negative 8 for me? Tell me what you get. It's negative 2. Hang on, how does that work? Well, remember, what does x cubed actually mean? It means something multiplied by itself 3 times. And if you take negative 2 and you multiply it by itself 3 times, you do in fact get, well, negative 2 times negative 2 is positive 4, but then multiplied by negative 2 again, you get negative 8.
What a beautiful thing.
It is a beautiful thing. And that's solving cubic functions. How would we sketch something like this?
You don't sketch it.
What did we notice about this form? This form is really good for something. The x-intercepts. I know the x-intercepts. Now be careful because, yeah, you want to think about what value of x makes this equal to 0. X equals to 0 is one of them because if you just put a 0 here, this whole thing is going to be 0. X equals to 2 is one of them because 2 minus 2 is just 0. But then here you're like, oh, the value of x here that makes that part in the brackets equal to 0, that's negative 3. Now, here's the problem. With cubics, they have a general kind of shape. How do we remember them? You can either remember as, okay, if the positive should look like this, if this was negative, right, how would that look like? Well, that would be the same thing, but just the other orientation. Right, so it's kind of something like this. I think it's a bit hard to remember because there's so many things you have to remember. You want a more robust way of treating that. Okay, rather than trying to do that, we want to see the general behavior of this curve. And we call this the limiting behavior. We essentially want to check, okay, what's happening at really large values of x? So Sam, can you put in for me in your calculator? Put in this equation like when x equals to 100. And Joel, can you put in for me when x equals to like negative 100 into this equation here? So right now, it's kind of like a table of values, but we're testing the values at really large, we're testing the behavior at really large values. So if you put in x equals to 100, What do you get? What kind of number?
6 digit.
6 digits, but what kind of number is it? It's a negative number. So we can say when x is, so I asked you for negative 100. If you put in larger and larger negative values, like this will still continue to happen. If x is approaching negative infinity, so really large values over here, what's your y approaching? It's approaching negative values as well, right? So that's negative infinity as well.
What do you get, Sam?
What did you get, Sam? Yeah.
10 million.
Again, if x is approaching a big infinity, what's your y approaching? It's approaching a big positive infinity as well, right? We call this the limiting behavior. And this is how you can use to sketch, sorry, it's a bit sideways. You can use this to sketch graphs by looking at what's happening at these large values. The way we represent that is saying, okay, I'm going to have an arrow going like this. Because if x is really large, your y is really large too. But what's happening on the other side? Well, if x is really large negative, y is also really large negative. Now in this form, we call these single roots, okay? Because the powers are just 1 for each of these roots here. We're going to look at different forms later. But all you need to know about this kind of form is that when we pass through each of these roots, I know these are all my roots here, when I pass through all of them, it's literally just going to cut them, like so. And you're essentially just kind of like matching up the dots here, if you do it properly, right? So you know where your cubic needs to end up for these large values, and you know it has to pass through all these roots in this way, and that's how you can construct your cubic there, okay?